All right, welcome back. So we've written the code, now what? This is where the real magic happens. We're going to talk about turning that abstract design into an actual physical piece of silicon. How in the world do you go from a language that just describes what something should do to a microchip you can hold in your hand? Well, let's get into it.
Okay, so here's the game plan for how we're going to break this down. First, we'll look at how that blueprint gets turned into actual gates. Then, we get into what I like to call planning the Silicon City. After that, we hit a really important fork in the road, two very different paths you can take. And finally, we'll dig into why you might go custom. Sound good? Let's go.
All right, so everything kicks off with our blueprint, which is written in a language like VHDL. Now, it's super important to understand what VHDL is and what it isn't. It's not a programming language like Python or C++. It doesn't give a step-by-step list of commands. No, instead, it describes hardware. It's all about explaining how different parts are connected and what they're supposed to do.
Yeah, this is what's called a behavioral description. Think of it like this. You're just saying, hey, when the clock ticks, I want this value to get stored in memory. See? You're describing the outcome you want. But you haven't said a thing about the actual logic gates, the ands, ors, nots that have to be arranged to make that happen. So our first big job is translating that what into a very concrete how.
And that's where this incredible process called logic synthesis comes into play. You know, the best way to think about it is like a special compiler, but for hardware. It takes our high-level, sort of abstract VHDL description, and it translates it all into a super detailed schematic of logic gates. What comes out the other end is something called a netlist. And that's just what it sounds like, a list of all the components and a map of how every single one is wired together.
But here's the really cool part. Synthesis isn't just a dumb one-to-one translation. Oh no, it's this complex optimization puzzle. The software is constantly trying to balance these three often competing goals. Like, imagine you're designing a chip for a smartwatch. What's most important? Do you want the smallest possible area to make the watch sleek? Or is low power the top priority so the battery lasts for days? Maybe you're willing to give up some top speed, the delay, to get that. The synthesis tool has to juggle all these trade-offs to hit the targets the designer set.
Okay, so we've got our netlist, we have all our individual building blocks. Great. Now comes the next massive challenge. Where do we put everything? We have to arrange all these gates on the actual silicon die. And this is exactly like city planning. We're about to lay out a whole metropolis, from the big downtown districts all the way down to every single suburban house. This whole thing breaks down into three main stages, and each one gets more and more detailed, building on the one before it. We're going to start with the big picture and then just keep zooming in until every last wire is in place.
So first up, floor planning. This is the 30,000-foot view. We're deciding where the big districts of our Silicon City are going to go. You know, stuff like the CPU core over here, the main memory blocks over there, and the I/O pads around the edge. The whole point is to put things that talk to each other a lot right next to each other. You want the main data highways between them to be as short and fast as possible.
Okay, after floor planning, we have placement. And if floor planning was about the districts, placement is about deciding where every single house goes. We're talking about each individual logic gate. We're getting super granular now, putting every gate from our netlist into its exact spot within its neighborhood. And finally, routing. This is where we connect everything up. It's a really complex task that's actually done in two parts. First, there's global routing. Think of this as planning the major highway system for our city. It just figures out the general paths. Then comes detailed routing, which gets right down to the nitty-gritty. This is where we lay the actual local streets, the specific metal wires and power lines that connect every single house to its neighbors and to the city's power grid. So, there we have it. Our Silicon City is all planned out. Every building has a plot of land, all the roads are mapped, but now we face a huge decision. How do we actually build this city? Because the choice we make right now is going to determine the final physical form of our chip.
Really, the fundamental question boils down to this. Are we going to build our city on a pre-existing grid, like a planned community where the streets are already there, or are we going to build it completely from scratch, paving every single road and pouring every foundation ourselves?
And that choice leads us to the two big players in modern digital design. FPGAs, that's our prefabricated city grid, and ASICs, that's our completely custom-built city.
So let's take a look at the final steps down each of these very different paths. They might start from the same blueprint, but believe me, where they end up is worlds apart.
Okay,
So with an FPGA, the key thing to remember is the physical chip already exists. It's a generic, off-the-shelf piece of silicon that's designed to be reconfigured. Our whole design process just generates what's called a bitstream. It's basically a file of ones and zeros. And when you load that bitstream onto the FPGA, it acts like a set of instructions that literally rewires the internal connections to create the exact circuit we designed. It's not fabricating hardware, it's programming hardware.
Now, the ASIC path is the total opposite. Here, you're creating a brand new chip from the ground up. The final output file is something called a GDSI. This is the master blueprint, the file you send to the factory. It contains the exact geometric shapes and patterns for every single layer that will be built onto the silicon.
And the moment you send that GDSI file to the foundry, that has a name. It's called tape-out. And this is a huge deal in any project because it is the absolute point of no return. Once you tape out, that's it. The design is locked in and the incredibly expensive manufacturing process kicks off.
And that finality, it's a really big deal. Why? Because as our source material points out, creating the manufacturing masks from that GDSI file costs a fortune. These masks are basically the stencils the founder uses to etch the patterns onto the silicon wafers. And if you have a mistake in your design at this point, we're talking about a mistake that can literally cost millions of dollars.
So all of this brings up a really crucial question, one that pretty much every hardware designer has to ask themselves at the start of a new project.
I mean, think about it. If FPGAs are so flexible, and you can reprogram them, and they're way faster to get up and running, why would anyone ever go through the expensive, time-consuming, and totally permanent process of making a custom ASIC? Well, the answer comes down to performance and cost, but with a huge asterisk, only at massive, massive scale.
Look, if you're just prototyping something or making a small number of devices, FPGAs are absolutely the way to go. But what if you're Apple and you need to make 200 million chips for the next iPhone? Suddenly, the economics totally flip. That huge upfront cost to design the ASIC gets spread across all those millions of units, and the cost for each individual chip becomes way, way lower. And on top of that, because an ASIC is custom built for one job and one job only, it is always going to be faster and more power efficient than a generic do-everything FPGA.
So there you have it. That is the incredible journey all the way from a few lines of abstract code to a physical crystal of silicon. And it leaves us with this really interesting question about the future, right? As our world demands more and more speed, more and more efficiency, which path is going to define what's next? Will it be the speed and flexibility of reconfigurable hardware like FPGAs? Or will our constant, insatiable demand for just a little more performance, a little more battery life, always lead us back to crafting perfectly optimized, custom-designed silicon? The answer to that is probably going to shape a whole lot of the technology we'll be using in the years to come.